Imagine for a moment that you were standing on this incredibly freezing, just windswept deck of a wooden naval ship.
Oh, that sounds miserable.
Right. It's the year 1818. You are somewhere out in the icy waters of Baffin's Bay, which is off the coast of Greenland, and you're searching for the Northwest Passage.
So, literal edge of the known world at the time.
Exactly. And for hours, your crew has been hauling up this thick, heavy-sounding line from a depth of over 1,000 meters. It is, back-breaking, brutal work.
Doing that by hand is just unimaginable today.
Yeah, completely manual. So finally, the brass weight reaches the surface, and clinging to the rope, pulled from a depth that every single educated scientific mind on the planet guarantees is this crushing, frozen, utterly dead abyss, is a massive, writhing, multi-armed starfish.
A literal living creature from the dead zone.
Exactly. So you bring it back to the greatest scientific institutions in the world. You place this undeniable physical proof right on the table in front of them. And do you know what the entire scientific establishment says?
I do, and it is still infuriating.
They look at the starfish, they look at you, they basically say, nope, doesn't count. You must have accidentally snagged it near the surface because there's absolutely nothing alive down there.
Which is, the reaction to that starfish is honestly one of the most stunning examples of cognitive dissonance in the history of biology. I mean, the dogma of the dead ocean was so incredibly powerful that physical reality simply bounced right off of it.
It really did. So welcome to today's deep dive. I want you to get comfortable, put away your preconceptions, and let your imagination sink to the very bottom of the sea with us, because we are unpacking a truly fascinating stack of sources today.
We really are. It's a great lineup.
Yeah, we are looking at the actual historical logs of Victorian-era marine biology, the modern expedition data from the staggering 5 Deeds mission, a massive morphological study out of UC Davis, and the absolute latest impact reports from the ocean census.
And, the overarching narrative connecting all of these sources is this profound paradigm shift. We are basically tracking how humanity's understanding of the deep ocean flipped from a scientifically endorsed, mathematically proven dead zone into the realization that it is, in fact, the most vibrant, bizarre, and biodiverse frontier on our planet.
And our mission for you today is to explore exactly how that happened. Because as we're going to see, this is not just a story about weird fish.
Right, not at all.
It is a story about human psychology. It's about confirmation bias. It is about how brilliant people can, completely blind themselves to the truth. And ultimately, it's about how the complete absence of light rewrites the fundamental rules of evolution.
Right. And to truly appreciate the life we now know exists in the deep ocean, we first have to understand the immense psychological and, frankly, institutional barriers that prevented us from seeing it in the first place.
We really do.
We have to understand why, for decades, the absolute smartest people on Earth were convinced the bottom of the ocean was just an empty void.
Okay, let's unpack this. Take us back to the beginning of this delusion. Where does this dead zone idea actually officially start?
Well, we have to travel to the mid-19th century and look at a man named Edward Forbes.
Okay, Edward Forbes.
Yeah, he was this brilliant naturalist from the Isle of Man, born in 1815. And today, he is widely considered the founder of British marine biology. Forbes was the kind of person who was just utterly captivated by the natural world from childhood.
Like a prodigy kind of situation.
Sort of, yeah. I mean, by the age of 12, he had constructed a natural history museum inside his own home. He collected everything: minerals, fossils, dried seaweeds, shells, you name it.
That is such a classic Victorian gentleman scientist origin story.
Oh, very much so. He originally wanted to be an artist, actually, but the Royal Academy in London refused to admit him.
Oh, wow.
So yielding to family pressure, he went to the University of Edinburgh to study medicine. But his heart was just never in the medical ward. He spent every spare minute pursuing natural history, and his particular obsession became dredging the seabed.
Which brings us to the year 1841. He manages to get himself assigned to the HMS Beacon, right?
Yes, exactly.
This is a surveying mission heading to the Aegean Sea in the Eastern Mediterranean, under the command of Captain Thomas Graves. Now, I really want to set the scene for you listening, because it is crucial to understand the physical limitations of what they were actually doing.
It's so important.
It's 1841. The Royal Navy is just beginning to experiment with steam power, but the Beacon is a traditional sailing vessel. So they are relying on the wind, and more importantly, they are relying on human muscle.
Right, and the physical labor involved in 19th century marine biology cannot be overstated.
Yeah.
I mean, when we talk about dredging, we are talking about throwing a heavy iron frame attached to a net or a bag over the side of the ship, letting it sink all the way to the bottom, and then literally dragging it along the seafloor to scrape up whatever is down there.
And then they have to haul it back up by hand. There are no electric winches. It's just sailors pushing massive wooden capstans, walking in endless circles, hauling hundreds of fathoms of soaked, heavy rope and a dredge filled with, rocks and mud.
It was exhausting, truly agonizing work. Yet over the course of an 18-month expedition, Forbes and the crew managed to execute over 100 hauls of the dredge.
Wow, 100 times.
Yeah, and they managed to reach depths of about 230 fathoms.
Let me just do the math on that real quick. A fathom is 6 feet, so 230 fathoms is roughly 4,380 feet, or about 420 meters deep.
Correct. And as the dredge came up, the captain's cabin was transformed into this makeshift floating laboratory. Forbes would meticulously sort through the mud, dissect the animals, sketch them with the artistic skill he had honed in his youth, and preserve the specimens in jars of alcohol.
Right.
But as he cataloged the hauls day after day, month after month, he began to notice a very distinct pattern.
And this pattern is the seed of the Great Delusion. What exactly was he seeing?
Well, he observed that the biological hauls were becoming progressively poorer the deeper the dredge went. So he started categorizing the Mediterranean seabed into distinct depth zones.
Okay, like layers.
Exactly. At the very top, you had the littoral zone, right along the shore, which was dominated by seaweeds and just teeming with life. Below that was the laminarian zone, full of large brown kelps, fish, and countless invertebrates.
So that's the bustling coastal metropolis.
Precisely. But then, as they dredged deeper into what he called the coralline zone, the plant life began to decline dramatically as the sunlight faded. And finally, when they dredged down to 230 fathoms, which was the deepest zone they could reach, the hauls were incredibly sparse. He was really only finding a few struggling sponges and the occasional mollusk.
So he looks at this data, right? Abundant life at the surface, less life in the middle, and almost no life at 400 meters. And he makes a massive logical leap. I am looking at his actual writings from the source material, and he states, the number of species and of individuals diminishes as we descend, pointing to a zero in the distribution of animal life as yet unvisited.
That's the quote, yeah.
He literally charts a graph in his mind, draws a line pointing downward, and declares that at exactly 300 fathoms, which is about 550 meters, life hits absolute zero.
And he gave this theory a formal scientific name, the azoic hypothesis.
Azoic.
Yeah, azoic comes from Greek, literally meaning without life. He proclaimed that below 300 fathoms, the ocean was just a barren, empty void. And the truly astounding part is that the global scientific community read his hypothesis, nodded in agreement, and basically accepted it as absolute biological law.
But wait, why would they just accept that? I mean, he didn't even dredge past 230 fathoms, he just guessed what happened next. Why did the entire scientific establishment blindly agree with an untested guess?
It seems crazy now, but it's because the azoic hypothesis perfectly aligned with the broader scientific philosophies and terrestrial observations of the era. You see, the scientific community of the 1840s was heavily influenced by the work of the famous German naturalist Alexander von Humboldt.
Ah, the man who basically invented the concept of ecosystems.
Exactly him. Between 1799 and 1804, Humboldt traveled extensively through Latin America, and one of his most famous achievements was climbing Mount Chimborazo in the Andes.
Right.
As he climbed, he meticulously recorded the changes in flora and fauna. He demonstrated that at sea level in the tropics, you have this explosion of biodiversity, palms, bananas, dense jungles, but as you hike higher up the mountain, the temperature drops, the air thins, and the vegetation changes to pines and oaks.
And then as you keep climbing toward the freezing summit, the trees disappear entirely, the plants vanish, and you are left with nothing but barren rock and ice.
Precisely. Humboldt proved that extreme terrestrial environments extinguish life. So when Edward Forbes suggested the exact same thing was happening in the ocean, it felt intuitively correct to Victorian scientists.
It just made sense to them.
Exactly. They looked at the deep sea and reasoned that as you descend, the temperature plummets toward freezing, the sunlight completely vanishes, and the physical weight of the water creates unimaginable pressure.
So they basically looked at the ocean and said, oh, it is just an upside-down mountain.
That is the exact mental model they used. In fact, a renowned Swiss-born naturalist named Louis Agassiz stated this parallel explicitly. He wrote, "The depths of the ocean are quite as impassable for marine species as high mountains are for terrestrial animals."
Wow.
Yeah. Agassiz and others focused heavily on the pressure aspect. A geologist named David Page even mathematically calculated that water at a depth of just 1,000 feet is compressed by 1,340th of its bulk.
Hold on, I need to push back on this because it sounds like they thought water pressure acts like a giant hydraulic press.
Yeah.
Did they actually think the water would just squash a fish flat? Like, how did they think pressure worked biologically?
They absolutely did. The assumption was that the sheer mechanical force of the water column above would be so immense that it would collapse any biological structure.
Just flatten it.
Yeah, they believed that the delicate tissues, the internal cavities, and the very cellular membranes of an animal would be ruptured and literally crushed into an unrecognizable paste by the weight of the ocean.
Okay, but we know today that the deep ocean is completely full of fish. So how do they actually survive that pressure? Because clearly Agassiz was wrong, but the physics of thousands of tons of water pressing down is still real. How does a fish not get crushed?
The Victorian scientists failed to understand that marine organisms are mostly made of water themselves, and water is largely incompressible.
Oh, right.
The internal pressure of a deep-sea fish matches the external pressure of the ocean. They don't have large, gas-filled cavities like the swim bladders found in many shallow water fish, which would indeed collapse.
So they aren't really fighting the pressure, they are just letting it flow through them, so to speak.
At a macro level, yes. But the true danger of deep-sea pressure isn't getting squashed like a tin can. The real danger happens at the molecular level.
Okay, how so?
Extreme pressure forces water molecules tightly together, which actually crushes the proteins inside a fish's cells, preventing those proteins from folding correctly and doing their jobs. And if your proteins stop working, you die instantly.
That is terrifying. So how do they stop their own proteins from mangling?
They utilize specialized molecules called pisolites. The most common one in deep-sea fish is called TMAO, which stands for trimethylamine N-oxide.
TMAO.
Yeah, TMAO acts like a microscopic scaffolding. It binds to the water molecules inside the fish's cells, creating a protective buffer around the proteins. It physically holds the space open, resisting the crushing weight of the ocean, allowing the proteins to fold and function normally.
That is incredible. And incidentally, looking at our notes, TMAO is the chemical that gives fish that strong fishy smell when they start to decay.
It is, yeah.
So the deeper a fish lives, the more TMAO it needs to survive the pressure, which means deep-sea fish probably smell incredibly strong if you bring them to the surface.
It's a fascinating and completely accurate biological byproduct, but of course Edward Forbes, Louis Agassiz, and their contemporaries knew absolutely nothing of molecular pisolites or cellular scaffolding. They only knew the crude physics of weight and temperature.
But even without molecular biology, they should have known their physical sampling methods were deeply, deeply flawed. I mean, I am looking at the historical descriptions of Forbes's dredge. They were trying to sample the deep ocean floor using a canvas bag. A literal canvas bag with few tiny eyelet holes punched in it.
The equipment was staggeringly inadequate for the task.
It is maddening. Just think of the physics of that. You drop a canvas sack 400 meters down. The moment it hits the seabed, it fills with heavy, dense mud. The tiny eyelet holes immediately clog. So for the next 3 hours, while the sailors are breaking their backs, hauling it up, this bag isn't catching any marine life.
Nope.
It is just a sealed sack of mud being dragged through the water. It is literally like trying to capture a rare, delicate butterfly by swinging a heavy, soaking wet burlap sack through the air, completely failing to catch anything, and then proudly declaring to the world that butterflies do not exist.
Your frustration is entirely justified, and it perfectly illustrates a crucial philosophical concept in the history of science called the theory-ladenness of observation.
Theory-ladenness. Break that down for us.
The term was popularized by the philosopher of science N.R. Hansen in the mid-20th century. The core idea is that human observation is never purely objective. What we see, and more importantly, how we interpret what we see, is heavily burdened or laden by the theoretical beliefs we already hold.
Ah, I see.
When Forbes pulled up an empty canvas bag, a truly objective observer might have said, well, this bag is clogged with mud, our tool is broken. But because Forbes already believed the deep ocean was a dead zone, his brain interpreted the empty bag not as a tool failure, but as absolute confirmation of his pre-existing theory.
He saw exactly what he expected to see.
Exactly. The theory acts as a filter on reality. And the danger of theory-ladenness isn't just that it makes you misinterpret bad data. The real danger is that it makes you actively ignore highly accurate data that contradicts your worldview. And the Victorian scientific establishment ignored a mountain of undeniable physical evidence.
This is where the story gets really wild. Because as we mentioned right at the top of the show, they actually had the proof. It was literally slapping them in the face, and they just waved it away. Take us back to that starfish in Baffin's Bay.
Right, that was Captain John Ross in 1818, over 2 decades before Forbes even proposed the azoic hypothesis. Ross was an experienced Arctic explorer. He wasn't using a canvas dredge, he was using a sounding line equipped with a heavy snapping device called a deep-sea clam.
Spelled with 2 M's, right?
Yes, CLAMM. It was designed specifically to bite into the seabed and bring up a sample.
And he drops this down incredibly deep.
He reported the depth as 800 fathoms. Now, modern analysis suggests it might have been closer to 600 fathoms due to the angle of the ropes and the current. But regardless, that is well over 1,000 meters down. It massively exceeds Forbes' 515-meter limit.
Right.
And when Royce hauled the clam back up, entangled in the sounding line was a spectacular specimen of a basket star, Gorgonocephalus arcticus.
A complex, living, breathing animal from over a kilometer deep. So how on earth did the scientific community brush that off?
Through character assassination and technical pedantry.
Oh, wow.
Yeah. When Ross returned to the UK, his expedition was marred by a completely separate controversy. Ross had turned his ships around in Lancaster Sound because he claimed he saw a massive range of mountains blocking the path, mountains he named the Croker Mountains. But his second-in-command, William Edward Parry, insisted the mountains were a mirage. Later expeditions proved Parry right, the mountains didn't exist.
So Ross's reputation as an observer was completely destroyed.
Precisely. If a man sees fake mountains, why should we trust his depth measurements? Furthermore, the naturalists in London pointed out that the starfish came up wrapped around the rope, not secured inside the jaws of the deep-sea clam.
Oh, so they found a loophole.
Exactly. Therefore, they argued, it was highly probable that this basket star was just a free-swimming animal living in the warm surface waters that merely snagged the rope as it was being pulled up.
Which is such a desperate, reaching assumption to protect their own dogma. But okay, maybe you can dismiss one starfish and one discredited captain, but it happened again, didn't it? What about George Charles Wallich?
The Wallich case is even more egregious. Fast forward to 1860, the Industrial Revolution is booming, and there is a massive push to lay transatlantic telegraph cables. Survey ships are crisscrossing the ocean to map the seabed for these cables. George Charles Wallich was a naturalist aboard the HMS Bulldog, surveying the waters midway between Greenland and Rockall.
And he is taking soundings, too.
Yes. They pull up a sounding line from a staggering depth of 200 and 260 fathoms. That is roughly 2,305 meters deep.
Wow.
2.5 kilometers down into the abyss. And attached to the final 50 fathoms of that rope were no fewer than 13 brittle stars.
13?
13 intact, living starfish. Wallich was overjoyed. He immediately grasped the magnitude of what he was looking at. He explicitly wrote that this discovery proved the absolute fallacy of the azoic hypothesis. He declared that an entirely new series of creatures must be peopling the deeper abysses of the ocean.
I mean, you cannot argue that 13 bottom-dwelling starfish all simultaneously decided to go for a mid-water swim and synchronized a trapeze catch onto a single rope. It is statistically impossible. So how did the establishment ignore 13 starfish?
By dismissing the man himself, Wallich was known to be a brilliant but highly irascible, difficult, and abrasive character. He rubbed the scientific elite the wrong way.
Office politics.
Essentially, yes. Specifically, he was locked in bitter rivalries with 2 prominent figures at the Royal Society, Charles Wyville Thomson and William Carpenter. Because Wyville Thomson and Carpenter held the social and institutional power, they simply brushed Wallich's findings under the rug. They ignored his papers and excluded him from the mainstream scientific discourse.
It is so incredibly human, isn't it? I want you, if you're listening to this right now, to really reflect on this dynamic in your own life or your own industry. How often do we completely ignore glaring, factual evidence right in front of us just because it contradicts a deeply held assumption? Or, even worse, how often do we dismiss a brilliant idea simply because we do not personally like the tone of the person delivering the message?
It is a universal human flaw, but in this case, it actively paralyzed the advancement of marine biology for a quarter of a century, and the evidence just kept piling up.
Yeah.
Also, in 1860, a telegraph cable spanning the Mediterranean Sea broke. To repair it, an engineer named Fleming Jenkin had to haul the broken cable up from a depth of 1,200 fathoms.
Well, let me guess. It wasn't clean.
The section of the cable that had been resting on the seabed was completely encrusted with marine life. It was covered in solitary deep-sea corals, oysters, and tube-building worms.
Wow.
These were animals permanently cemented to the cable. There was no possible way to argue they had snagged the line on the way up. They had lived their entire lives 1.5 miles underwater.
And still, the scientific consensus barely budged. Which brings us to an inevitable breaking point. To shatter a deeply entrenched scientific dogma, you cannot just theorize. You cannot just argue in drawing rooms in London. You have to go out into the ocean and physically drag an overwhelming, undeniable volume of truth up into the light.
Which is exactly what the establishment figures, Wyville, Thomson, and Carpenter, the very men who ignored Wallich, finally decided to do. The pressure from the telegraph companies, who needed to know what the seabed was actually like to protect their massive financial investments, provided the necessary funding and political will.
Smony talks.
Always. Wyville, Thomson, and Carpenter secured the use of Royal Naval vessels from the Admiralty.
They start with the HMS Lightning, which the sources describe as essentially a floating rust bucket.
It was famously described as a cranky little vessel, quite possibly the oldest paddle steamer still active in the Navy at the time. But it allowed them to start testing the waters between Scotland and the Faroe Islands in 1868. Then, in 1869 and 1870, they secured a much stoudier, better-equipped ship, the HMS Porcupine, and they dredged the deep waters off the British Isles, the coast of Spain, and into the Mediterranean.
But hold on, if they're going back out on ships, they are still facing the fundamental physical problem of the Victorian era. They're still using dredges. So weren't they still just pulling up bags of mud? How did they solve the burlap sack problem?
The mud problem persisted, yes. The deep-water dredges were heavy, unwieldy, and frequently came up empty or hopelessly clogged with sediment. The scientists were struggling. But the true hero of this story, the man who finally broke the azoic hypothesis, wasn't a fellow of the Royal Society.
Okay, who was it?
It was the captain of the HMS Porcupine, a practical seaman named Edward Kilwick Calver.
What did Captain Calver do?
Calver was an observant man. He watched the scientists hauling up these useless mud-filled bags, but he noticed something the scientists missed. While the inside of the dredge bag was empty of life, occasionally small sea urchins, echinoderms, corals, and sponges would be brought to the surface clinging to the outside of the bag, tangled in the frayed ropes that held the iron frame together.
Because they weren't getting smothered by the mud inside. The rough fibers of the rope were snagging the spiky exteriors of the animals.
Exactly. Calver recognized the mechanism immediately. So he approached the scientists and suggested a brilliant, almost comically simple modification. He ordered the crew to take thick lengths of hemp rope, untwist them, tease out the individual fibers until they were frayed and bushy, and then attach these massive bundles of frayed rope to the outside of the iron dredge frame. They called these contraptions hempen tangles.
So they essentially strapped a fleet of giant, heavy-duty underwater mops to the sides of the dredge.
A perfect analogy, and the results were devastatingly effective. By dramatically increasing the surface area of fibrous material dragging across the ocean floor, the hempen tangles bypassed the mud problem completely. When they hauled the dredges up from depths of 650 fathoms, 1,000 fathoms, and beyond, the tangles were absolutely choked with life.
Amazing.
They snagged hundreds of delicate sea creatures, many entirely unknown to science, pulling them up intact from the freezing dark.
I love that so much. A working-class ship captain, just looking at the practical reality of how frayed rope behaves, definitively solves a decades-old scientific debate that the greatest minds of Europe couldn't figure out. With hundreds of creatures laid out on the deck of the Porcupine, there was nowhere left for the dogma to hide. The azoic hypothesis was officially, undeniably dead.
It was a revolution. It proved the deep ocean was not a desert, but a vast, populated wilderness. But pulling up a mangled starfish on a mop from a mile down is one thing. Actually seeing that wilderness, actually visiting it, would require an unimaginable leap in technology.
Which is the perfect transition. Let's fast forward over a century. We go from dropping hemp ropes off wooden paddle steamers in the 1870s to the ultimate extreme in modern human exploration. I'm talking about the Five Deeps mission and the explorer Victor Vescovo.
The Five Deeps exhibition is arguably one of the greatest feats of modern engineering and oceanographic exploration. Launched by EOS expeditions, Triton submarines, and Vescovo himself, the ambition was audacious: to design a vehicle capable of reaching the absolute deepest point in all 5 of the world's oceans.
And to do that, they built a machine that sounds like it belongs in science fiction.
They collaborated with Triton submarines to build a highly advanced 2-person submersible called the Limiting Factor. Unlike previous deep-sea vehicles that were essentially massive, clunky elevators that could only go down and straight back up, the limiting factor was designed to be highly maneuverable.
How do you build something that can maneuver when the pressure is literally 1,000 times greater than at the surface? I mean, Agassiz was wrong about fish getting crushed, but he wasn't wrong about the physics. If a human in a submarine goes down there, the ocean desperately wants to crush them into a pulp.
The engineering is breathtaking. The core of the limiting factor is a perfectly spherical personnel cabin made of grade 5 titanium, nearly 4 inches thick. A sphere is nature's strongest shape against uniform pressure,
Right.
but titanium is heavy. If the whole sub were made of metal, it would sink like a stone and never come back. So the vast majority of the vehicle's bulk is actually made of specialized syntactic foam.
Syntactic foam, what is that?
It is an incredibly advanced buoyancy material. It is a solid resin matrix embedded with billions of microscopic hollow glass spheres.
Glass spheres.
Yes. It provides massive lift, but it will not compress or absorb water even at the absolute bottom of the ocean. This combination of a titanium pressure hull and syntactic foam buoyancy allowed Vescovo to take the sub to the absolute limit.
He took it to the Challenger Deep, located in the Mariana Trench, which is the deepest known point of the Pacific Ocean. He reached a confirmed maximum depth of 10,928 meters. That is nearly 11 kilometers straight down. You could drop Mount Everest into the Mariana Trench, and the peak of the mountain would still be over a mile underwater.
To give Vescovo's achievement some historical context, previous monumental dives to the Challenger Deep, like the famous descent by Don Walsh and Jacques Piccard in the U.S. Navy vessel Trieste in 1960, and film director James Cameron's solo dive in the Deep-Sea Challenger in 2012, those were isolated single descent events.
They just went down and came up.
Exactly. They went down, touched the bottom, and came back. Vescovo proved his engineering by undertaking 4 separate consecutive dives to the Challenger Deep in a single expedition. During his deepest dive on April 28, 2019, he spent 4 continuous hours driving along the bottom of the basin, actively mapping the terrain.
But while the Mariana Trench gets all the headlines for being the deepest, looking at the expedition logs, the dive that absolutely blew my mind was their mission to the Java Trench in the Indian Ocean.
Also known as the Sunda Trench, the 5 Deeps expedition was the first time a human had ever descended to the bottom of the Indian Ocean. The Java Trench is this immense, arc-shaped subduction zone about 3,200 kilometers long.
Wait, I assumed everywhere had been somewhat explored by unmanned drones at least. The bottom of the Indian Ocean was completely unvisited before this.
Completely unvisited by human eyes. The team descended to a depth of 7,192 meters. Heather Stewart, a marine geologist with the British Geological Survey who was part of the research team, highlighted the sheer scale of this. 7,192 meters is a depth more than 5 times the height of Ben Nevis, the highest mountain in the United Kingdom.
And what they captured on their 4K cameras down there is just stunning. They aren't just finding stray starfish. They found completely new species of Haddle snailfish gracefully swimming over the sediment. They recorded the deepest octopods ever seen by science. But the specific encounter that left the entire control room completely speechless was this incredible, bizarre, drifting creature they called an extraordinary gelatinous animal.
Taxonomists who reviewed the footage believe it was a stalked ascidian, commonly known as a sea squirt. But at that depth, its morphology was completely alien. It drifted past the titanium hull, resembling a translucent, ghostly balloon floating on a tether. It is a profound testament to how much biodiversity remains completely hidden from us.
But the biological life wasn't the only shock. The footage also revealed something incredible about the geological environment, which fundamentally changes how we understand the energy of the ocean.
Yes, it did. During the Java Trench dive, Vescovo steered the submersible up a towering 150-meter-high near-vertical escarpment. As they illuminated the rock face, they saw areas of massive debris where the bedrock had recently fractured and failed. And growing vividly within the deep cracks of these newly exposed rocks, they observed spectacular, sprawling displays of bright orange, vivid yellow, and stark white colors.
Okay, here's where it gets really interesting. I need to pause and ask a fundamental biological question. If you are 7,000 meters down, there is absolute pitch black darkness. There are no photons of sunlight reaching that rock. None. So what is the fuel source for this ecosystem?
It's the ultimate question.
Because every biology class I've ever taken says all life on Earth fundamentally relies on the sun. Plants make food from sunlight, herbivores eat the plants, carnivores eat the herbivores. I am picturing this vibrant underwater city on a cliff face, but there are no solar panels. So what power grid are they plugged into? Where's the energy coming from?
It is the perfect question, and the answer represents one of the greatest biological discoveries of the 20th century. There are two primary fuel sources operating in the deep ocean, and they represent completely different paradigms of survival. The first, older paradigm is what marine biologists call marine snow.
Which sounds incredibly romantic and beautiful, but the reality is actually a bit gross, isn't it?
It is entirely unromantic. Marine snow is the continuous, gentle shower of organic detritus falling from the sunlit upper layers of the ocean down into the abyss.
So it's the scraps falling from the table of the surface world.
Exactly. It is composed of dead algae, microscopic phytoplankton that have lived out their life cycle, fecal matter from pelagic fish, and the decaying fragments of larger organisms. As this material slowly drifts down, sometimes taking weeks or months to reach the bottom, it clumps together into white, flaky aggregates.
Thus the snow.
Right. This marine snow is the foundational food source for the vast majority of scavengers, detrivores, and mud sifters living on the deep sea floor. Interestingly, the critical importance of marine snow was first theorized way back in the 1870s following the Great Challenger expedition, which was the massive global survey that immediately followed the success of the porcupine's hemp tangles.
Okay, so marine snow explains how a scavenger crab survives. It just eats the falling garbage. That still fundamentally relies on the sun because the sun grew the algae at the top. But what about those vivid orange and yellow patches on the rocks in the Java Trench? They aren't catching snow. What is the second power grid?
The second power grid is called chemosynthesis, and this is the paradigm-shattering discovery. Those bright colors on the escarpment rock face were not minerals. They were massive, thriving bacterial communities, and they do not rely on sunlight whatsoever. They rely on the chemical fluids oozing from the cracks in the Earth's crust.
So it is like a deep-sea geothermal power plant. Instead of solar panels on the roof capturing photons, they've got cables plugged straight into the Earth's mantle, drawing energy from the planet itself.
That is an excellent analogy. We see chemosynthesis most dramatically at hydrothermal vents, often called black smokers, and cold seeps. At these sites, seawater seeps down into the Earth's crust, becomes superheated by underlying magma, and dissolves massive amounts of minerals from the rocks. When the superheated, chemical-rich fluid erupts back out into the freezing ocean water, the minerals precipitate out.
But how does a bacteria actually eat a chemical? How does chemosynthesis work chemically?
The bacteria living at these vents possess specialized enzymes. They take inorganic molecules erupting from the vent, most commonly hydrogen sulfide, which is highly toxic to surface life, or methane, and they oxidize them.
Okay, so they process the toxins.
Right. By stripping electrons away from the hydrogen sulfide and combining it with dissolved oxygen in the water, the bacteria generate the chemical energy needed to convert carbon dioxide into organic sugars. They are literally manufacturing biological food out of toxic volcanic gas.
That is just staggering. It is life powered by the internal geologic friction of the Earth itself. The Earth is bleeding chemical energy into the dark, and these ecosystems are drinking it up.
And the biological implications are profound. Because these bacteria form the base of a food web, they support entire ecosystems of larger animals. Giant tube worms, eyeless shrimp, specialized crabs that graze on the bacterial mats or actually host the bacteria symbiotically inside their own bodies. It fundamentally rewrote our understanding of the constraints of life. If you remove sunlight as an absolute requirement, the boundaries of biology expand exponentially.
Which brings up a massive point about evolution. If you permanently remove sunlight and you completely change the primary fuel source of an ecosystem, you dramatically change the evolutionary pressures on the animals that live there. You are throwing out the old rule book and writing a new one. So how does the pitch black darkness physically shape a living creature over millions of years?
To answer that question scientifically, we turn to a fascinating and incredibly rigorous study published out of UC Davis. The research was led by postdoctoral researcher Christopher Martinez, working in Professor Peter Wainwright's laboratory in the Department of Evolution and Ecology. They utilized the massive, globally sourced database from the Smithsonian National Museum of Natural History to ask exactly that question. How does depth change shape?
The sheer scale of this study is wild. They didn't just look at a few anglerfish. They analyzed over 8,000 individual specimens. Those specimens represented 3,033 completely different species of fish, categorized by where they lived: shallow coastal waters, the intermediate twilight zones, and the deep abyssal ocean.
To understand the differences objectively, they had to move beyond simply looking at the fish and describing them. They took highly detailed, standardized mathematical measurements of every specimen. They measured body length, body depth, the width of the fish, head depth, mouth width, upper and lower jaw length, and the precise dimensions of the caudal peduncle.
Wait, what is a caudal peduncle?
It is the narrow part of a fish's body just before the tail fin. Its thickness is a massive indicator of how much muscle mass a fish dedicates to rapid, powerful swimming.
Okay, so they take thousands of physical measurements. What do they do with all that data?
They feed it into complex statistical models to plot every single species into a two-dimensional mathematical diagram called a morphospace.
Explain morphospace. I am picturing a giant scatter plot graph on a whiteboard.
That is exactly what it is. Imagine a graph where the axes represent different combinations of these body measurements. A fish that is long and skinny gets plotted in the top left. A fish that is short and fat gets plotted in the bottom right. By plotting all 3,033 species onto this morphospace, Martinez and his team could visually see how body shapes clustered together based on the environment they lived in.
And the results show a massive, undeniable divide between the surface world and the deep world. Let's look at the shallow water fishes first.
The morphospace revealed that shallow water fishes generally cluster very tightly around a similar average body shape. If you picture a standard red snapper or a bass, you are pretty close to the mathematical average.
But when you look at the deep ocean fishes plotted on the graph, the cluster just explodes outward in every direction. They display a vastly wider variety of shapes. You have everything from wildly elongated, ribbon-like creatures like the snipe eel to these incredibly globular, squat, nightmare-inducing monsters like the deep-sea anglerfish. Why such a drastic difference?
If we connect this morphospace data to the bigger environmental picture, it makes perfect evolutionary sense. Let's think about the selective pressures of shallow water. In a sunlit coral reef or a coastal shelf, sight is the primary sense. A fish has to be able to hunt visually at relatively long distances, or conversely, it has to spot a predator from far away and escape quickly.
Plus, shallow water isn't still. They have to constantly swim against tidal currents, navigate around complex rock formations, and deal with wave action.
Precisely. All of those physical and biological factors create a very strict evolutionary funnel. It puts a massive survival premium on powerful, efficient locomotion. To survive in shallow water, a fish generally needs to be highly streamlined. It needs to be aerodynamic or technically hydrodynamic.
That makes sense.
If a random genetic mutation creates a fish that is a weird, slow, uncoordinated bulbous shape in a coral reef, that fish is going to be eaten by a shark immediately. Or it will starve because it cannot chase down a minnow, or it will simply get smashed against a rock by the surf. The environment ruthlessly calls anything that isn't built for speed and agility.
So shallow water is basically like a high-speed Formula One race. Every single competitor needs a sleek, aerodynamic car just to stay on the track. If you bring a tractor to an F1 race, you lose. But the deep ocean is a completely different game. It is like a slow-motion bumper car arena played in the pitch dark.
I love that comparison.
Yeah, because speed doesn't matter anymore. You can be whatever weird, bulbous, elongated shape you want, as long as you have one specific feature, a giant mouth.
Your F1 versus bumper car analogy captures the biomechanical shift perfectly. In the abyssal depth, it is permanently, utterly black. Encounters with prey or encounters with predators do not happen at a distance. They happen blindly, at extremely close quarters, usually when two organisms physically bump into each other or sense minute vibrations in the water just inches away.
So there is no high-speed chase.
None. Therefore, powerful, fast swimming isn't nearly as important. In fact, large swimming muscles are a liability because they require immense amounts of calories to maintain. The deep sea, away from the chemosynthetic vents, is a notoriously resource-poor, starving environment. Energy conservation is the ultimate rule of survival. You want to expend as little energy as biologically possible, hovering silently in the dark, waiting for a meal to wander by.
When that meal finally bumps into you in the dark, you cannot afford to miss, because you don't know if you'll find another meal tomorrow or next month, which beautifully explains the one major finding in the UC Davis study. Despite the massive explosion of weird body shapes, the morphospace analysis found one unifying physical trait across all these wildly diverse deep-sea oddities: extraordinary jaw length.
Precisely. Deep water fishes generally do not have small mouths. Evolution has prioritized the oral cavity above almost all other anatomical features. Because meals are so rare, when a deep-sea fish senses prey, its mouth needs to act like an inescapable, instantaneous trap. Many species possess huge jaws lined with inward-facing, needle-like teeth, combined with hyper-expandable stomachs. It ensures that whatever they bump into, Even if it is a fish nearly their own size, it does not get away.
It is the ultimate evolutionary playground. Because the darkness and the cold remove the normal hydrodynamic constraints we see on the surface, the deep ocean has allowed evolution to go completely wild, experimenting with anatomical forms that would never survive in the sunlight. We literally went from Edward Forbes thinking it was a barren frozen desert to realizing it is likely the most bizarre, species-rich environment on the entire planet.
And the truly staggering, humbling reality is that despite all our technology, we're only just now beginning to actually catalog the extent of that biodiversity.
That brings us out of the history books and right up to the present day. I want to look at the monumental efforts of the Nippon Foundation Nekton Ocean Census. This is a global initiative with a singular urgent mission: to accelerate the discovery of ocean life, to advance fundamental science, and empower immediate marine conservation.
And they are executing that mission at an unprecedented scale. According to their latest impact report, in just a single year, the Ocean Census Initiative discovered 11,121 new marine species.
Over 1,000 new species in 12 months.
Yes. That single-year total marks a staggering 54% jump in the annual rate of marine species identification globally. But even with that massive leap forward, marine biologists estimate that up to 90% of ocean species still remain completely undiscovered by science.
Think about that. 90% of the life in the ocean doesn't even have a name yet. It is a staggering amount of unknown biodiversity. And to find them, the Ocean Census is running a massive collaborative global effort. They have conducted 13 major expeditions across incredibly remote ocean regions. They are partnering with massive scientific organizations like JAMSTEC in Japan, the CSIRO in Australia, and the Schmidt Ocean Institute, running high-tech species discovery workshops all over the world.
The logistics of it are incredible.
So, what does this all mean for the future of science? We are out there finding all these incredible things. 1,121 species in a year is an amazing statistic, but I understand there has historically been a massive bureaucratic bottleneck in the scientific community. If we are pulling up thousands of new creatures from the deep, how do we actually keep track of it all? Because the stereotype of taxonomy is that a specimen just ends up sitting in a jar of formaldehyde on a dusty museum shelf for decades before anyone looks at it.
Your stereotype is unfortunately rooted in historical fact, and this raises a very important question about the structural nature of scientific classification. Historically, there has been an average lag of 13.5 years between the moment a scientist physically pulls a new species out of the ocean and the moment it is formally described, named, and published in the scientific literature.
13 and a half years. Why on earth does it take so long?
Because the traditional taxonomic process is incredibly archaic and meticulous. Let's say you pull up a bizarre new worm in the Pacific. First, you have to physically mail the fragile specimen to a museum. Then you have to find the one or two taxonomic experts on Earth who specialize in that specific family of worms. Those experts are likely backlogged with hundreds of other specimens.
Right.
When they finally get to it, they have to physically dissect it under a microscope, compare its jaw structures to centuries of older literature to ensure it is actually new, write a lengthy physical description, commission illustrations, and then submit that paper to a taxonomic journal.
And then it has to go through the slow grind of academic peer review before it is finally printed.
Exactly. And in the context of modern environmental threats like climate change, deep-sea trawling, and potential deep-sea mining, 13.5 years is an eternity. A deep-sea species could literally be discovered, its habitat destroyed by a mining operation, and the species driven to total extinction in the gap between the time we pull it out of the water and the time we finally give it an official name.
You cannot protect something if the law doesn't officially recognize that it exists. So how is the Ocean Census fixing this? How do you break a 13-year academic bottleneck?
They are breaking it by aggressively dragging marine taxonomy into the digital age with a new technological platform called Novio.
Okay, how does Novio actually work? Is it an AI system? A new database?
It is a comprehensive digital taxonomy infrastructure built on open access cloud architecture. Novio fundamentally changes the workflow. Instead of mailing a physical jar across the world and waiting years, when a new species is brought aboard a modern research vessel, scientists immediately put it through high-resolution 3D CT scanning. They take microscopic digital imaging of its anatomy. And crucially, they immediately extract its DNA and run genetic barcoding right there on the ship or at an affiliated workshop.
So they create a perfect digital and genetic twin of the animal.
Precisely. They create what is essentially a digital holotype. All of that data, the 3D models, the high-res photos, the full genomic sequence is instantly uploaded to the Novio platform. Novio creates a systematic, transparent, and globally accessible database. Because of this, Discovered is now being recognized as a formal open access status in its own right, long before a formal paper is printed. The collected data on a new species can be made available to researchers and policymakers globally within weeks or even days.
That completely changes the game for conservation. If a mining company wants to dredge a seamount, policymakers can look at Novier and immediately see, wait, we just found 50 unique species living exactly there last month. You cannot mine there. It bridges the knowledge gap immediately, providing the vital, real-time science required to enforce international agreements like the High Seas Treaty and global biodiversity frameworks.
It democratizes the data. It moves marine biology from a slow, cloistered academic exercise into a dynamic, real-time tool for planetary management.
I want to spend some time talking about the actual creatures they've recently rushed through this new system because the specific discoveries are just mind-blowing. Let's look at the ghost shark, also known as a chimera.
A phenomenal discovery. This was found by taxonomist Dr. William White during a CSIRO expedition to the Coral Sea Marine Park off the eastern coast of Australia. They brought it up from a depth of over 800 meters.
I am looking at a picture of it and it looks incredibly strange. It has these massive, dead-looking eyes, huge pectoral fins that look almost like wings, and this weirdly smooth skin. And it's not even a true shark, right?
That is correct. Chimeras are cartilaginous fish, meaning they have no bones, only cartilage, much like sharks and rays, but they are a distinct, distant branch of that family tree. What is truly incredible about the ghost shark is its evolutionary pedigree. Their specific evolutionary lineage diverged from sharks nearly 400 million years ago.
400 million years. That predates the first dinosaurs by a massive margin.
By nearly 160 million years. They survived the extinction event that wiped out the dinosaurs. They survived the shifting of the continents. They retreated into the deep, dark ocean, and they have remained there, largely unchanged, haunting the abyssal plains as living fossils. Finding a new species of chimera is like finding a new chapter in the oldest history book on Earth.
And then there is the discovery in Japan, the Delhasiella yabuki.
This is a beautiful example of deep-sea ecology. It was discovered on the Shichio seamount chain at 791 meters deep. Taxonomically, Delhasiella yabuki is a species of polychaete worm, commonly known as a bristleworm.
But it isn't the worm itself that is so fascinating. It is where it chooses to live. It lives inside a glass castle.
Yes, it is a highly specialized symbiotic worm that makes its permanent home exclusively inside the intricate internal chambers of a deep-sea glass sponge.
Okay, we need to pause and explain what a glass sponge is, because when I first read that, I thought it was a metaphor.
It is entirely literal. Glass sponges, or hexactinellids, are a class of deep-sea animals whose skeletons are constructed entirely of structural spicules made from crystalline silica. They extract silicic acid from the seawater and biomanufacture literal glass. They weave this glass into incredibly complex, lattice-like structures, vases, tubes, and intricate geometrical cages that look like delicate fiber optic sculptures.
That sounds like something out of a high fantasy novel. A bristle worm living in a glowing glass castle at the bottom of the ocean. The worm gets a fortified, predator-proof home, and the sponge presumably benefits from the worm keeping the internal chambers clean of debris. It is a perfect micro-ecosystem.
And it highlights how deep-sea animals do not exist in isolation. They have evolved deeply complex, interwoven relationships over millions of years.
Finally, let's talk about the ribbon worm found in Timor-Leste.
The Drepanophoridae family. Now, this creature was actually found in much shallower waters, between 1 and 5 meters deep along the coast.
Which is a great reminder that while the deep abyss is vastly unexplored, we don't always need a titanium submarine to find unknown life. We are still finding incredible things right off the beach. Tell us about this worm.
This ribbon worm is physically diminutive, measuring less than 3 centimeters long. However, what it lacks in size, it makes up for in visual impact. It possesses vividly bright, striking pigmentation patterns across its body.
And anyone who watches nature documentaries knows that when you are tiny, slow, and brightly colored, it usually means one thing to predators: do not eat me or you will regret it.
Precisely. In evolutionary biology, we call this aposematism. It is a visual warning signal advertising potent chemical defenses. Ribbon worms are well known to marine biologists for possessing incredibly complex, highly toxic venom cocktails, which they use both to subdue their prey and to deter fish from eating them.
And this specific point, the complex toxins of marine life, is exactly why you, the listener, should care deeply about all of this, because this entire conversation isn't just an intellectual exercise in cataloging weird biology so we can have more pictures in a textbook. It is highly immediately practical to your life. those specific complex toxins found in the ribbon worm. They are currently being investigated by leading biomedical scientists for their pharmaceutical significance. Specifically, they are being researched as potential foundations for new treatments for severe neurological conditions, including Alzheimer's disease and schizophrenia.
The ocean represents a massive, largely untouched reservoir of novel complex biochemistry. Because marine organisms, especially in the deep sea, have evolved in such extreme, highly competitive, or totally unique environments, they've been forced to develop chemical compounds, defensive toxins, and metabolic enzymes that simply do not exist anywhere on land.
The rainforest gets a lot of credit for pharmaceutical discoveries, but the ocean is vastly larger and infinitely weirder. Protecting the deep ocean isn't just about saving a weird-looking ghost shark or a glass sponge. It is a literal treasure map for humanity's future medical breakthroughs. Every single time we destroy a deep-sea habitat with indiscriminate bottom trawling, or every time a corporation begins deep-sea mining for battery metals before we have even mapped the biology of the seamount, we might be permanently destroying the cure for a major human disease before we even know it exists. Oliver Steeds, the director of the Ocean Census, put it perfectly. He pointed out the disparity in our scientific funding. He said we spend billions upon billions of dollars sending rovers to search for microscopic, fossilized evidence of past life on Mars, or looking at the dark side of the moon. But discovering the vast majority of vital, living, breathing life on our own planet costs a fraction of that.
It is entirely a question of societal priorities. We are choosing to look outward before we have fully understood the critical life support systems of our own home.
Which makes this the perfect moment to take a breath and recap the incredible journey we've been on today. We started in the 1840s with Edward Forbes and his perfectly logical but completely spectacularly wrong azoic hypothesis, believing with absolute certainty that the deep ocean was a crushed, frozen dead zone. We followed Victorian captains snagging starfish on frayed hemp tangles to shatter that scientific dogma. We rode modern titanium submarines down 11 kilometers into the crushing pressures of the Mariana and Java trenches with Victor Vescovo and the Five Deeps mission. We discovered an alien oasis on a rock wall, powered not by the sun, but by the Earth's internal chemistry through chemosynthesis. We explored the UC Davis morphospace to see how pitch-black darkness shapes creatures into beautiful, terrifying, huge-mouthed monsters optimized for energy conservation. And finally, we looked at how the Ocean Census is utilizing the digital Novier platform to catalog this vital medical treasure trove at record speed before we lose it.
It is a monumental shift in human understanding, representing one of the greatest scientific awakenings in history. And I want to leave you with a final thought that builds directly on what we discussed about chemosynthesis and the extremophile bacteria living on those deep sea vents. We talked about how the Earth bleeds chemical energy into the dark ocean, supporting a massive food web without a single photon of sunlight. Now, I want you to project that biological reality outward, back into space exploration. We spend billions building massive telescopes, looking at distant stars, constantly wondering if life exists on exoplanets far from our sun in what we call the habitable zone. But look at our own solar system. Look specifically at Jupiter's moon, Europa.
Europa is a frozen moon. It is entirely encased in a shell of ice miles thick.
Yes, the surface is frozen solid. But beneath those miles of surface ice, planetary geologists are almost certain that Europa hides a massive, global, liquid saltwater ocean. It is pitch black, and it receives zero sunlight. For a very long time, astrobiologists assumed it must be a dead, sterile ocean. But the discovery of the deep ocean here on Earth, the realization that life thrives in the freezing dark, sustained entirely by chemosynthetic hydrothermal vents, provides the exact proven blueprint for extraterrestrial life.
Because Europa isn't geologically dead, is it? It has tidal heating.
Exactly. The immense gravitational pull of Jupiter constantly squeezes and stretches Europa as it orbits, creating internal friction. That friction generates massive internal heat in the moon's core. If that active core is interacting with the bottom of Europa's subsurface ocean, there are almost certainly hydrothermal vents down there, spewing the exact same chemical soup we see in the Java Trench. We might not need a massive space telescope to find alien life. The deep ocean proves that life doesn't need a sun. It doesn't need a warm summer breeze. It just needs water, basic minerals, and a chemical spark from a planetary core. We just needed a better submarine to find those aliens right here at home, and in doing so, the deep sea has given us the exact coordinates of what to look for out there in the dark of space.
That is an absolutely chilling and beautiful thought. The extraterrestrials we are desperately looking for in the stars might look an awful lot like the eyeless shrimp and ghost sharks swimming right now in our own abyssal trenches. What an incredibly profound stack of sources today. Thank you so much for sitting down and joining us on this deep dive. As always, keep questioning your deepest assumptions. Keep pushing past the blank spaces on your own maps and keep diving deep into your curiosities. We will catch you next time.